paper.com, Linda has wrote amazing materials, including the breezes from EDU, and she's wrote really interesting, and the report also on electromagnetic processes of binary black hole mergers. Today, she can tell us about her latest work, electromagnetic flares and solid processes of stars. Thank you.
So thank you very much for coming and for inviting me. As Phil said, the title of my talk is Electromagnetic Flares from the Tidal Disruption of Stars by Massive Black Holes. And this is work that I'm doing with my advisor that I acquired at Berkeley. So the story I'd like to tell you is about hungry massive black holes in the centers of galaxies and poor unsuspecting stars that occasionally wander too close to them. So close, in fact, that the difference in the black hole's gravity between the near side of the star and the far side of the star exceeds the binding gravity holding the star together. And so the star disrupts, and a fraction of stellar gas spirals down into the black hole, releasing a flare of electromagnetic energy, as we can in principle observe. We can work out what the size is of this danger disruption zone around the black hole by setting equal the star's binding gravity and the black hole's tidal gravity. And we get that for solar type stars, which is what I'll be focusing on, the tidal radius is of order in AU. We can learn something important by looking at the scaling of the tidal radius with black hole mass, which from this equation is our tidal grows as black hole mass to the 1/3 power. Contrast that with the Schwarzschild radius, the size of the event horizon, which grows as black hole mass to the 1st power. Those two different scalings have the consequence that for a 10 to the 5 solar mass black hole, kind of the smallest black hole you can imagine lives in the center of a galaxy, those black holes can tidally disrupt stars far outside the black hole's event horizon, at like 100 Schwarzschild radii. But as you go to more and more massive black holes, the tidal radius is growing only slowly, while the event horizon is growing quickly, and above about 10 to the 8 solar mass black holes, the event horizon actually lies outside the tidal disruption radius. And so these most massive black holes don't tidally disrupt stars at all, but they instead just swallow them whole. And so if you want to get an electromagnetic flare from the tidal disruption of a star, 10 to the 5 to 10 to the 8 solar masses is basically the sweet spot. Now, gravitational interactions between stars ensure that this process must happen at least sometimes in the nucleus of any stellar system with a not too massive black hole. And so we can, in principle, use this process of tidal disruption of stars as a tool for studying black holes in galactic nuclei. In particular, it can help us to study the demography of black holes in quiescent galaxies, help us learn about stellar dynamics in galactic nuclei, and help us understand how massive black holes grow. So tidal disruption flares offer a new probe, a new way of detecting black holes in distant quiescent rather than active galaxies, perhaps as far out as redshift 1, as we'll see. And maybe give us insights into the mass of the black hole. And in particular, it can give us information about black holes having masses in the lower mass range of 10 to the 5 to 10 to the 6 solar masses, where we otherwise don't have very much information. The demography of these black holes is unclear because their host galaxies are faint and the black hole has only a tiny radius of influence. Tidal disruptions also can teach us about stellar dynamics in galactic nuclei. So the basic mechanism for taking a star and putting it on a trajectory aimed at the black hole is through gravitational perturbations with other stars. And through just that mechanism, the tidal disruption rate in a spherical nucleus is the number of stars at the radius of influence of the black hole divided by the relaxation time there. But on top of that basic baseline mechanism are other enhancing mechanisms, like perhaps having a flattened potential rather than a spherical one, or even a triaxial potential, which would lead to chaotic orbits, or maybe stars interact often with giant molecular clouds, or maybe resonant relaxation is an important process. And so, due to all these different possible processes, theoretical estimates for the tidal disruption rate per galaxy range by orders of magnitude, from like 10 to the -5 per year up to 10 to the -3 per year. So that means that observationally measuring the tidal disruption rate will allow us to turn that around and teach us about the dynamical conditions close to the black hole. And then thirdly, tidal disruptions can help us understand how massive black holes grow. So most directly, we can learn about seed black holes potentially growing by consuming stars. So this could be particularly important for these lower mass black holes, like a 10 to the 5 solar mass black hole. So if the rate per galaxy is this conservative 10 to the minus 5 per year, and such a black hole is able to accrete a good fraction of the solar mass of material that's being fed to it, then over a Hubble time, a 10 to the 5 solar mass black hole can grow by its own mass. And this is particularly interesting because it ties the growth of the black hole to dynamical conditions further out in the stellar bulge, and maybe offers us some insight into the M-sigma relation. And then additionally, probably primarily, see black holes grow by accreting nearby gas. But the details of how that accretion works aren't fully understood, and so tidal disruptions offer us a clean lab for studying accretion physics, because we think we have some idea about what the mass of the material and the dynamics are of the material that's being fed to the black hole. And so we might, in particular, hope to learn the answer to the question of what happens when the feeding rate is super Eddington, because as we'll see, that's the relevant parameter range for most tidal disruption events. And so in particular, we'd like to learn what fraction of the gas actually gets accreted onto the black hole and can contribute to its growth, whereas what fraction gets blown back out. So with these astrophysical applications in mind, we'd love to go off and start detecting tidal disruption events and start using them as a tool to learn about black holes. And so to do that, we need to answer questions like how can we detect tidal disruption flares and what are their observable properties? And these are the questions I'm working on for my thesis, and so that's what I'm going to be talking about. So to get started, I need to tell you a bit more about the process of disruption itself. So the idea is that a star will typically approach from far outside the tidal radius on a zero-energy orbit, moving at the escape velocity from the black hole. And when the star reaches the vicinity of the black hole, it disrupts. And so it ceases to be a bound object anymore, and is now a bunch of different parcels of gas living in the black hole's potential well. And different parcels lie at slightly different depths, which corresponds to dramatically different fates. So schematically, the outer half is a little bit shallower in the black hole's potential well. So it ends up with positive specific energy. That material becomes unbound from the black hole and escapes on hyperbolic trajectories. So here's the black hole, then something like this orange curve. And then the other half of the material is a little bit deeper in the black hole's potential well. So it ends up with negative specific energy, and it becomes bound to the black hole. So it goes off on an elliptical orbit, but it eventually returns back to the black hole again. And it's that bound material that really powers the electromagnetic flare. So that's what I'm going to be focusing on, although I'll also mention observational properties of the unbound material as well. So following that bound material, after a time t fallback that's of order hours to weeks, the most bound material has gone off on its elliptical orbit, and now it's coming back to the black hole. And when it gets there, it shocks on itself and starts to accrete inwards. And then hot on its heels is material that's a little bit less bound to the black hole on a slightly longer period orbit, more energetic. And behind that is material in an even longer period orbit. And so by knowing what the distribution is of energy within the material that we used to comprise the star, we can work out what the rate is of mass falling back to the black hole, m dot fallback. And that's of order m star over t fallback initially, and then declines with time as t to the minus 5/3. Now it's this quantity, m dot fallback, that's all important for determining what the observable properties of a tidal disruption event will be. In particular, what matters is the comparison with the Eddington rate, because that tells us how important radiation pressure is as opposed to gravity. So here I'm plotting the ratio m dot fallback over m dot Eddington as a function of time in days for a 10 to the 6 solar mass black hole disrupting a star at the tidal radius. And what you see is that after about 10 days, the fallback rate reaches a maximum of several hundred times the Eddington rate. And then over the subsequent months and years, it declines with time and eventually becomes sub-Eddington. As the fallback rate declines with time, the observable properties go through two different phases of evolution. While the fallback rate is super Eddington, the physics is uncertain, but there's likely to be an advective accretion disk accompanied by powerful outflows. And then once the fallback rate becomes sub-Eddington, the gas accretes through a thin accretion disk. Now, based on these considerations, several observational searches for tidal disruption events have been conducted already. And so far, they've mostly been focusing on the emission from this accretion disk. So the typical basic suppositions that go into these observational searches are, as I said, to focus on the accretion disk, which should be brightest in the soft X-rays to UV. So those are the wave bands where people have been looking for tidal disruptions. And people also typically make the assumption that the flux in the observing band will decline as L mu proportional to m dot fallback, which is proportional to t to the minus 5/3. And as we'll see, that is not a justified assumption, because to get the actual time dependence, you need to figure out what the time evolution of the temperature and of the emitting area of the gas is. But that's the assumption that most of these have made. And so the strategy is to look back through data that's already been taken. These are archival searches looking for a large amplitude brightening that happens only once. And that's to cut out the major contaminant to this kind of search, which is going to be active galactic nuclei, AGN. And then to further rule out AGN, once a candidate has been identified, it's followed up with an optical spectrum to make sure that there are no AGN emission lines. So far, these types of observational searches have yielded a handful, maybe a dozen candidate detections. So most of these are from the Rosa et al. Sky Survey and the XMM SLU Survey at X-ray wavelengths, and also from the Galactic Imaging Survey at UV wavelengths. And then very recently, the first optically selected tidal destruction candidates have been announced in the Slow Digital Sky Survey Stripe 82 and from the Palomar Transient Factory. And I'll return to these optically selected events at the end of my talk. So to show you more about how these observational searches so far work, I'm showing you an example of a UV selected candidate event from Galactic. So on the left is the is the light curve for the event. Magnitude is a function of time in years. The purple and black points are the far UV, the near UV and the far UV points from Galactic, which is how the event is identified. But there also is coincident CFHT optical data in G, R, and I band. And what you see is that at the end of 2004, the flare turns on, and then it declines with time over the subsequent years. The event reaches a maximum optical luminosity of a few by 10 to the 41 ergs per second, and a far UV luminosity of a few by 10 to the 43 ergs per second. So then once the candidate was identified, it was followed up with an optical spectrum, which I'm showing here. And you can see it shows only stellar absorption features, and so it's probably not an AGN. Additionally, there's X-ray data for this event. So it turned out that XMM was looking in the direction of this galaxy prior to the flare and didn't detect any X-rays. So again, it's probably not an AGN. And then after the flare, the Chandra looked and did detect X-rays. So this is basically the state of the art so far for the kind of data that we can have for a tidal disruption candidate. And based on significantly sparser data from the Rosa et al. Sky Survey, Donnelly et al. Were able to use the 3 events found with Rosat to estimate the tidal disruption rate per galaxy of order 10 to the minus 5 per year. And that agrees with conservative theoretical estimates as well. Other surveys since then have made similar estimates of the rate, getting maybe 10 to the minus 5, maybe 10 to the minus 4 per year, but they're based on similarly few events. And so all this observational work have been very important first steps, but they really suffer from severe limitations. Primarily that the searches are archival through slow cadence data, so there can be little or no real-time follow-up of these events, which means that there are only a few photometric data points, limited wavelength coverage, and no real-time spectra. And additionally, the searches probe only a small spatial volume, which leads them to find only a small number of candidate events. However, this could all be about to change with the advent of a new generation of transient surveys, with several new Rapid-Cadence Wide-Field Surveys, and I'll be focusing on the optical, although there are planned and started surveys at other wavelengths as well. So currently underway is the Palomar Transient Factory, which is a collaboration between Caltech and Berkeley and several other institutions, which is imaging a quarter of the sky down to magnitude 21 every few days. Then there's also Pan-STARRS, whose 3-pi survey is imaging 3-pi of the sky deeper than PTF, down to magnitude 23, but only every few months. And then there's the Medium Deep survey, which is imaging just a small spatial area, but very deeply, down to magnitude 25, and often every few days. And then in the coming decade, we can look forward to the Large Synoptic Survey Telescope, LSST, which should combine depth, cadence, and spatial area to image half the sky down to magnitude 24.5 every few days. And so these are going to revolutionize what we know about transients. And the question for tidal disruptions is, are they going to be important optical sources? Are we going to be able to learn about them based on these new optical transient surveys? So the first place to look could be the accretion disk. So here I'm plotting the spectral energy distribution, mu units per second, as a function of wavelength and energy from an analytic model of a thin to slim accretion disk. And this is as a function of time for a 10 to the 6 solar mass black hole disrupting a star's tidal radius. And the accretion disk emits as a multicolored black body, which is peaking at about 100 eV or 100 angstroms. While the fallback rate is super Eddington for 10 days, 30 days, 100 days, you can see all the green curves lie on top of each other, and the disk luminosity is roughly constant at the Eddington luminosity. And then once the fallback rate declines below the Eddington rate, the disk cools and fades with time for 1 year, 3 years, 10 years, and 7 years. However, the whole time, the optical emission is only down here, like 10 to the 40 or 10 to the 41 Earths per second, which is only a modest fraction of the brightness of the whole galaxy. And so this is going to be difficult to find tidal disruptions based on the emission from the accretion disk. Although on top of that, you can see there are some faint emission lines from the photoionized surface of the unbound debris, which could produce an interesting spectroscopic signature. So I'm going to take a moment to tell you about how that works. So the idea is that here's your accretion disk, and photons from the accretion disk shine on the unbound material, that stuff that's going off on hyperbolic trajectories, and photoionize the surface, which then emits at longer wavelengths and produces an emission line spectrum. So I used the photoionization code cloudy to figure out what that spectrum would look like. And here's the result for a 10 to the 6 solar mass black hole disrupting a star at 3 Schwarzschild radii, so fairly close to the event horizon, as a function of time. And what you see are the important lines are like the Balmer lines, Lyman alpha, also carbon-4. And so these are similar to the lines that you find in the broadline region of an active galactic nucleus, because the physical conditions are similar. However, the gas is too dense for there to be forbidden lines, unlike the narrow line region of an AGN. And so this looks like a broadline region with no associated narrow line region. Additionally, the lines are extremely broad because this gas is racing away from the black hole at a good fraction of the speed of light. And because it's asymmetrical, depending on your viewing angle, it can have a large redshift or blue shift away from the galactic line. So this could be an important spectroscopic signature once a candidate has been identified to identify this as actually a tidal disruption event. But even these lines are maybe only 1% above the galactic brightness. And so again, they're going to be hard for actually detecting tidal disruptions in the first place optically. Really the place to look for optical emission is these powerful outflows during the super Eddington phase. So the idea is that while the fallback rate is really high, the density of pericenter is high, and so photons that are produced at the shock are trapped there by electron scattering. The matter is so dense that most of the photons aren't able to diffuse out, and so radiation pressure drives the gas back outwards in an outflow that then we'll see has a large photosphere and produces a lot of optical emission. So to figure out what the photon spectrum from this outflow looks like, we need to start by figuring out what the photon spectrum at the shock is, because those are the photons that eventually make their way out and that we get to see. So this is a little cartoon to show you how we calculate what the photon spectrum at the shock is. So time proceeds from the left to the right. And in the first panel, we have falling back stellar debris, which has a lot of ordered kinetic energy because it's moving towards pericenter at a good fraction of the speed of light. But it's fairly cold, and so there are not many photons. Then the gas shocks and converts that ordered kinetic energy into random kinetic energy. And since the gas is moving so quickly, now the gas is very hot. But so far, there are only few photons. And then over time, free interactions produce more and more photons. And so eventually, the photons in the gas are able to reach thermal equilibrium. There are many photons around. The gas is able to cool, so it's not as hot, and the photons have attained a black body spectrum. So this picture works if the density at the shock is high enough for frequent free interactions, and then you get a black body photon spectrum. However, if the density at the shock is too low, then free interactions don't have time to produce enough photons to reach thermal equilibrium before radiation pressure from the few photons that there are pushes the gas back out again. And so in that case, we don't have thermal equilibrium. And instead, there are only a few photons, but the gas particles are moving fast, and so so the photons can't enough scatter off the electrons and produce a hard X-ray spectrum instead of a black body spectrum. So we expect this to happen eventually for any tidal disruption system, because eventually the fallback rate will get low enough and the density of periscope will get low enough. So for a 10 to the 6 solar mass black hole disrupting a star at the tidal radius, this should happen after about 2 weeks. And as you go to more and more massive black holes, this happens earlier and earlier. And for a 10 to the 7 solar mass black hole and above, we expect this to happen the entire flare. So I'm going to focus on the black body emission that we get at early times for lower mass black holes for now, and then I'll return to what these hard X-rays do to the predictions that I'm showing you.
So, in that, don't you make some assumption on the actual shape of the returning flow?
Yeah.
You make this kind of assumption?
I'm assuming that it's coming back spherically.
And the whole spherical?
Yeah, which is probably not
no model
greatest.
for the stream, and you understand you don't do that.
No. And that would help. So that would make the density a bit higher, and so that would make it happen a bit earlier. Yeah.
So if I understand the model, the densities and characteristics are the same, the time scale is different depending on the mass of
The densities are lower too for the higher mass black holes.
I'm just thinking about the tidal density of the star and one of the photon.
Right. Right, because the time scale for the materials to go back is longer. Yeah. Okay. So to recap that, the idea is that photons produce the shock, have a black body or a hard X-ray spectrum, and then electron scattering traps them. So the trap heat should do two different things. It should unbind some of the gas and drive an outflow, and it should be dragged along with the gas through an accretion disk into the black hole, as we already looked at. And you can see how both of these processes can go on at the same time by having outflowing gas along the pole and a slim accretion disk in the midplane, which is the original orbital plane of the star. This is borne out by numerical simulations. So here I'm showing you a radiation hydrodynamic simulation of black hole feeding at 100 times the Eddington rate from Asuga and Miyashige. And this plot from their paper shows the black hole here, and this is the radial coordinate, and here's the vertical coordinate. And the different colors correspond to different radial velocities in units of the freefall velocity. So along the polar axis, the color is white, which means radial velocity is greater than the freefall velocity. So that's gas that's unbound and escaping from the black hole. And then in the midplane, the radial velocity is slightly less than 0, and so that corresponds to accretion going into the black hole. And they find that roughly 10% of the material leaves in this unbound outflow. So to figure out what the outflow should actually look like observationally, we devised a simple analytic model to describe it. So we assume spherical geometry with a density profile that's rho of r is of order some fraction f out times m dot fallback divided by 4 pi r squared v wind, where typical values of f out might be like 10% based on that simulation I just showed you, and the wind velocity, a typical value, will be the escape velocity from the black hole at the point where the wind is launched, so close to pericenter for the star. So deep inside the outflow, the density is high, so the photons are trapped by electron scattering. The electron scattering optical depth is much larger than 1, and so the photon diffusion time is much greater than the expansion time. And so the photons aren't able to diffuse anywhere before they're just ejected out with the expanding gas. That means that the expansion is 80 fat, and so the temperature scales as rho to the 1/3 power, which gives us a way of calculating what the temperature is in the flow as a function of radius. Then eventually at the photosphere, the density is low enough that now the photons can escape. The optical depth to electron scattering is ordered unity, and so the photon diffusion time is less than the expansion time. The photons have a black body or a hard X-ray spectrum, as we said. And if they have a black body spectrum, then that's emanating from a large radius or a cool temperature. And so that gives rise to a large optical luminosity, which is exciting for optical transient observers. Then, as the fallback rate and the density decline with time, the photosphere moves deeper in, and so the temperature of the photosphere rises while the volumetric luminosity drops. So here's an example of what that looks like for a 10 to the 6 solar mass black hole disrupting a star at the tidal radius. So this is the spectral energy distribution. distribution as a function of wavelength or energy at 10 days, 30 days, and 100 days after disruption. So if you focus on the curve at 10 days, at that point the radius of the photosphere is large, it's 1,000 Schwarzschild radii, or 20 AU, while the temperature of the photosphere is a relatively cool 30,000 Kelvin. And so a good fraction of the overall luminosity comes out in optical wavelengths, giving rise to an optical luminosity that's of order 10 to the 43 ergs per second, or magnitude minus 19 or minus 20. So this is really bright. This is as bright as a supernova, or as bright as a good fraction of a galaxy. So we really can get excited that optical transient surveys have the potential to be able to find these events. Additionally, the outflow gives us a color evolution signature that we can look for, which is, as I mentioned, as time goes on, you get to see deeper and deeper into the outflow. And so that gets hotter and hotter with time, as you can see from the 10 days to 30 days to 100 days, it's getting hotter. And so if the peak of the black body spectrum is close to your observing band, then that looks like getting bluer with time, or if it's far away, then that looks like no color evolution if you're off on the really Gene scale. And we'll see how that's important in a moment. And then additionally, the outflow gives another important signature, which is a spectroscopic signature. So the idea is that this is a diagram of the outflow. Here's the photosphere for electron scattering. And there's still all this gas outside the photosphere, though. But for photons at most wavelengths, that gas is optically thin. And so the photons just escape directly and produce the black body continuum that I was just showing you. However, at particular wavelengths, there are absorption processes, like photoionization and bound-bound transitions that will remove photons. And then there are emission processes of recombination and bound-bound transitions. And so this outer gas imprints a spectrum on the black body continuum. So to figure out what that will look like, I used the photoionization code cloudy to figure out the photoionization properties of this outer gas and to figure out what the important spectral lines would be. And then I put those together with an analytic picture for the line profile. And here is an example result. Again, a 10 to the 6 solar mass black hole, and this is 10 days after disruption. So the pink dashed curve is the black body continuum, and on top of that you can see all of these spectral lines. The outer gas is highly ionized, and so there are few or no optical lines, although from particular viewpoints, if the gas is denser or moving at lower velocity, there can be some more optical lines. But most of the lines are in the UV, in the far UV to EUV, at wavelengths less than 2,000 angstroms. And some common lines are like carbon-3, silicon-4, and carbon-4, which are similar to the lines that are important in the spectra of broad absorption line quasars as well, because the physical conditions are similar in both of these. The absorption lines are broad because the gas is moving at such a high velocity, and they have a strong blue shift. The reason that the absorption lines are blue shifted is the same as in a P-Cygni profile. So if you're the observer and you're looking up back at the continuum emission from the electron scattering photosphere, then all the absorption that happens along your line of sight will be in gas that's moving towards you, and so the lines are blue shifted. So this picture of broad blue shifted absorption lines in the UV can be something that we can look for with, to identify tidal disruptions among a bunch of candidate events. Now, so far I've been focusing on the black body emission at times when the shock is able to thermalize. But as I mentioned a few moments ago, if the density is too low at later times or for higher mass black holes, then the shock is not able to thermalize, and instead you have a Compton upscattered spectrum with hard X-rays. So if there are hard X-rays around, that dramatically changes what the spectral lines will be. So here is a result for incomplete thermalization at the shock, where we have a black body spectrum with a X-ray power law that reaches out to 100 keV in addition. And that hard spectrum so highly ionizes the outer gas in the outflow that there are no optical or UV lines at all. But instead, there are all these X-ray absorption features that we could look for instead to identify the event. And so what this shows us is that having simultaneous data, X-ray data with the optical spectroscopy will help to identify and interpret these events. So to summarize what I've told you so far, during the super Eddington outflow phase, during the super Eddington phase, the flow produces an outflow that produces a flare. It lasts for weeks to months. There's an optically bright black body continuum that becomes hotter or bluer with time, and it has a spectroscopic signature of blue shifted absorption lines in the UV. And then additionally, non-thermalization at the shock, which is relevant at late times or for higher mass black holes, should produce hard X-rays and a featureless optical to UV spectrum. So then what we did is compared the results for our outflow model with the parameters for these upcoming and currently operating transient surveys to predict what are the detection rates for these transient surveys going to be.
Well, quick question.
Yeah.
What determines the power law in that study?
So we just used a phenomenological model based on what AGN spectra look like, and I think the answer is so far unclear, but that's something that I would like to look more about.
So in AGN, they made some regulation of the constant lifetime function by constant flow. So that would work at constant depth for the order of maybe a little bit less. So in this case, what's the constant depth you deal with in the next survey?
Probably more like 10 or 100. So I'm not sure what that would be exactly.
You may get more of the read section.
Okay. Be interested to talk more about that. So for these upcoming transient surveys, I'm plotting the rate as a function, the rate per year as a function of black hole mass from 10 to the 5 to 10 to the 8 solar masses for the Pan-STARRS 3-pi survey, Palomar transient factory, and LSST. And the Pan-STARRS medium peak survey is an order of magnitude or so lower because the spatial area is so small. The cadence of these surveys is really important for finding tidal destruction events because they last only days or weeks. And so the fact that PTF has a several-day cadence makes up for the fact that it's shallower than Pan-STARRS, which is looking only every few months. And so both of these surveys should be sensitive to hundreds of events per year. And LSST should be sensitive to thousands of events per year, of which tens to hundreds could be in this 10 to the 5 to 10 to the 6 solar mass range, where we know relatively little about the black holes. You could think that past surveys could be constraining for whether these detection rates are actually reasonable, but supernova searches, for example, typically exclude galactic nuclei where things get very complicated, or if they didn't, they would have mistaken these events for AGN. And so they're probably not too constraining, and it's possible that these detection rates are really reasonable, and we are going to be sensitive to all of these events in the very near future. Unfortunately, being sensitive to lots of tidal disruption events isn't good enough. You have to be able to identify them amidst all the different transients that these surveys are going to be finding. And in particular, supernovae pose a particular challenge because they can have similar luminosity and time scale. So some potential discriminants are the evolution time scale. Tidal disruptions can be faster, particularly if you're disrupting the star fairly close to the black hole. And the color evolution. So as I mentioned earlier, tidal disruptions get bluer with time or have no color evolution as we see deeper and deeper into the hot outflow, whereas supernovae get redder with time. Now the most direct discriminant that you might think of would be high-resolution imaging. Tidal disruptions happen in the nucleus of the galaxy, and supernovae happen off the nucleus. However, what happens in real life is that you see a brightening in the center of a galaxy, and you don't know whether it was really truly in the nucleus or somewhat offset. And so to quantify how big a problem that is, we estimated what is the rate of supernovae within a typical transient survey spatial resolution of half an arc second and compare with the tidal destruction rate. So here is the rate of supernovae within half an arc second at the center of a galaxy at redshift 1, which is where most of the survey volume is. So that's where most of those hundreds of events per year that I mentioned would be coming from. And what you see is that for transient surveys, the rate per galaxy is almost 1 every 10 years, which is 10 to the 3 or 10 to the 4 times greater than this nominal tidal disruption rate per galaxy of 10 to the -5 per year. So this is particularly concerning. Higher resolution follow-up with HST or adaptive optics helps knock it down by a couple of orders of magnitude, but there's still a long way to go, and there's still a lot of supernova contamination. So probably a better strategy is to select events that are closer, like redshift of 0.1, where that half arc second spatial resolution corresponds to a smaller size. There'll be far fewer events. PTF will probably be sensitive to maybe 10 events per year instead of hundreds, but they'll be easier to identify. So if you're a redshift of 0.1, now the transient surveys are finding 1 every 1,000 years per galaxy, which is only 100 times as much as the tidal disruption rate. And with higher resolution follow-up with HST or adaptive optics, that cuts the supernova contamination rate to a factor of a few. But this is clearly going to be really tricky business. And so we really need all the discriminants that we can get. Two more important ones are X-ray detection. So as I mentioned, tidal disruptions can produce a lot in the way of X-rays, whereas supernovae tend to be quite faint in the X-rays. And spectroscopy. And I showed you the spectroscopic predictions that we're making for the outflow and also from the unbound material. And so I'd like to close by telling you about the future is now, and we are actually finding optically selected tidal disruption candidates for the first time. So this is results from the Sloan Digital Sky Survey, Stripe 82, from a paper by Van Velsen et al., which was submitted several months ago. And so here is the light curve for one of the 2 events that they found. And they have in the UG and R band, blue, green, and red, they have 10 data points each spanning about 2 months. They don't have very good constraints over when the flare actually began just because of the cadence of the survey. And then they have some Galactic points a year and a half or so after the event. So the event reaches a maximum G-band luminosity of order 4 by 10 to the 43 ergs per second for this example event, and the other one is fairly similar. The color is very blue, and there's no color evolution. They managed to get an optical spectrum shortly after they detected the flare, because it was thought to be a supernova initially, and they found a featureless continuum, and there's unfortunately no X-ray data on this event. So in their paper, they make a big deal about how this is too bright to compare well with the predictions from our outflow model, but that's actually not a correct interpretation of our model. And I think it's not completely clear that this isn't an unusual kind of supernova or AGN activity, but these properties are broadly in line with the predictions that we're making for the outflow of a tidal disruption event. And so if this truly is a tidal disruption, we're probably looking at the super Eddington outflow, and in order to get a large luminosity, there's probably a high fraction of the gas being blown out. So instead of a conservative 10%, maybe 50% of the gas that's flowing back is being blown back out again, or it's being blown out at a lower velocity. And so additionally, the Brad Senko at Berkeley has found a candidate event with the Palomar transient factory, and he's currently finishing analyzing and writing that up. So on the left, I'm showing you the light curve of the event. Black is I band, red is R band, and green is G band. These points and then these points are all upper limits. So it's these are the actual data for the event. And it's plotted as a function of time since discovery. And so you can see that the event faded quickly and then became undetectable after just a week. So this is a really fast evolution for a transient, which tells you that it's probably not a supernova, for example. The color is very blue, and it shows a featureless optical spectrum. They triggered SWIFT on the event, so they also have X-ray data and some far UV data. And they fit a black body spectrum to the optical and UV data, which is the solid turquoise curve, which has a cool temperature of 2 by 10 to the 4 Kelvin. You can ignore this turquoise dash curve. And then with an X-ray power law tail that extends out here. And the overall volumetric luminosity is order 10 to the 45 ergs per second. So again, it's not clear that this event isn't some unusual supernova or some unusual AGN, but again, the properties are broadly consistent with what we're predicting for the tidal disruption event. And so we can look forward to the not too distant future where optical detections of tidal disruption events are possible and exciting and commonplace. So in conclusion, I predict that new and upcoming transient surveys will detect many tidal disruption events. The super-Eddington outflows will likely lead to large optical detection rates for PTF, pan-stars analysis T. It's going to be challenging to identify and distinguish these from supernovae, but the color evolution will help. And so will the spectroscopic signatures of outflows, blue-shifted absorption lines in the UV, or X-ray absorption and a featureless UV and optical continuum if the shock isn't able to thermalize. And maybe the first optical discoveries have already been made. So we can look forward to time not too long from now when tidal disruptions are found all the time and are able to use as a tool to teach us about black holes and galactic nuclei. In particular, teaching us about the demography of black holes and quiescent galaxies, especially black holes at fairly low masses, teaching us about the stellar dynamics in galactic nuclei, and about how massive black holes grow. Thank you.
We have time for questions. Thank you once again.